Okay, good afternoon. So, yesterday I introduced myself as head of Teaching Learning Center. So, let me reintroduce myself. I am faculty in Chemical Engineering Department of IIT Bombay. I'm a professor in Chemical Engineering, and my area of working is broadly systems and control, process control. So, I'm also associate faculty with systems and control engineering. So I work in a interdisciplinary area which is on the borderline of multiple disciplines. So today I'm going to share with you my experience of teaching this particular aspect, model development using regression. So this is something which is needed in every branch of science and engineering, also in humanities, economics, social sciences. I'm not sure that there is any branch which is not touched by, except probably maybe in English. I admit you may not need this, but in literature you don't need regression. But most other branches, including humanities, you need to know about regression. Even if you do not know to sit and write down a program or understand it fully, you need to actually probably use it. Nowadays there are tools like Excel, which allow you to just upload data, get regression models without understanding fully mathematics behind it. Nevertheless, you need to use it and you need to know something about it. Okay. So this is something that I'm going to share, that how I do it. It has evolved over a period of time. I don't think when we started teaching this, it was active learning based delivery, but now over a period of time it has changed to active learning based teaching of this particular topic. So I'm going to talk about what is the motivation for this particular lecture. Okay, I'm going to avoid teaching regression, though some part will be come in the way, and some math slides are there, but I'm going to skip them. So I have uploaded two, if you are able to access Moodle, I have uploaded two levels of notes. One level of notes is what I'm presenting now. Okay, I would call it a meta level presentation, where I'm trying to reflect upon how I teach. Okay, what I teach, what is the content, is there in another set of notes, which are very detailed notes on regression, all the maths in gory details. If some of you are interested in knowing the maths behind the whole thing, you can look at those notes. Also, the two notes present a contrast. The detailed notes are the way, earlier I used to, or many of us teach conventionally, very dry, deductive, authoritarian style of notes. No attempt to make it active or anything. I'm just giving diktats that this is like this, this is like this. Whereas this is completely different. So the contrast also will be clear to you if you look at two different set of notes. One set of notes talk about how to make it active. The other set of notes is just like a deductive textbook, And I'm sure when students looked at those formidable notes, they said, my God, yet another maths course I have to do. So this is an attempt to get over that fear. Okay. So what I'm going to do is talk about what are the learning objectives. So first I'm going to give a motivation for this lecture. Okay, not the motivation for regression, or motivation for this lecture. Then I'll go to one of my first learning objective is creating a need to learn regression. Okay, I'm not going to start by teaching a regression formula. I'm going to first create a need to do this in the class through some activities, and then proceed to discuss about some issues in modeling. What happens? What are the difficulties? Okay, now we decide to develop a model from data. What happens? What are the issues that crop up? What you need to think about? Then we'll talk about estimating model parameters from data. So this is where algebra will come in. Some formulas will come in. And then, of course, once you give equations and formulae, you can develop an assessment plan for the students based on those formulae. And then the fourth objective that I want to introduce to the students as a part of this set of lectures is uncertainty modeling and its application. So I'm not going to talk about one lecture. I'm going to talk about a lecture plan. Okay. So this set of lectures, say 6 to 8 lectures spread over 2 weeks, interspaced with some activities, and part of it will be lecture, part of it will be activities. Like Professor Verma said yesterday, in maths, it is not, beyond the point, it's not possible to ask students to guess. Okay, you can't guess some proof of some theorem. You can prod them, you can take them close to thinking about something, but some things have to be taught on the board. Okay, so it has to be a mixture of both. Okay. So, I'll also talk about, while talking about each of these aspects, I'll talk about summative assessment, formative assessment, that is in-class assessment or in-class questions. And then what I do for doing exams, quizzes. What I have done in the Moodle is I have uploaded my tutorials, my quizzes, demo programs that I share with the students. Everything I have shared with you so that you get to see what all things that are made available to the students. And then we'll summarize. I have a large number of slides, and many of them I'm just going to skip, particularly ones in which there are too many formula, because that is not the aim of this lecture. Aim of this lecture is to talk about how I teach, not to teach you regression. Probably most of you have done regressions at some point or the other and use it. So that is the aim is to talk more about the approach to teach rather than. Okay. Now, where does this regression come? Okay. Now, what has happened is this is when we revised our curriculum, I think 7, 8 years back, we decided that data science is a very, very important area, and it must be taught to all engineers. All those who come to IIT Bombay, all students should be taught. It has a bit of a history. Now the question was, who should teach this course? The statistics course. Okay, and you start with basics of statistics, mean, variance, probability densities, hypothesis testing, standard things that any student should know, and then data fitting, model, regression. So this is the course which should be done by all engineers, okay, and all science students. In fact, we now have a program in economics, and it is must for them too. It's not that they can, so it's must for everyone. Now, for some reason, maths department did not start teaching this course. There were some maths faculty who were initially doing some help, but the course was being managed mostly by engineering faculty. And later at some point, it happened so that it was decided that this course will be taught by all engineering departments. Okay, so now data science course, that is statistics, probability statistics course, almost all departments have their own faculty teaching that course, and I think that's a very good thing. That is because, in fact, in chemical engineering, or I guess in MEMS too, numerical analysis or computations are taught in the department by the faculty. You will have a presentation today. So, importance of that is, when we engineers teach to our own students in a branch, then we can make it very relevant to our application area. We can bring in we can mix all the applications which are relevant to a particular area that makes the learning experience much richer than, just as a maths course in which they don't know why this is being taught. Okay, most of the students cannot learn when you say that, okay, believe me, this is going to be useful one day after 3 years. Right now, just remember this formula, give this exam. Okay, they are able to. Some of them are smart; they are able to pass the exams. I found other students who get stuck by saying that, oh, I don't understand this, and they shut their mind. Okay, and then once they shut their mind, you can't help them because then there is a problem. So we teach this course in which we teach parameter estimation, probability statistics, hypothesis testing, and then model development using regression. That's towards the end of the course. Okay, so that is where this particular course, because it deals with data, and nowadays there is some access to the computer to most of the students in elite institutes like IIT or even tech-funded institutes, which are all government institutes. There are reasonably, you can assume that some computer lab is available, or the students themselves have a laptop. So, okay. So now this module which I'm going to introduce, what are the learning objectives? What is it that I want to teach? Can we capture patterns observed in data using a simple algebraic equation? So there are patterns that are, when we actually look at some data of some cause and effect, can we actually capture those patterns? Okay. Given a data set, can I fit a polynomial? I'm going to, if I do it at a basic level for undergraduates, this is typically done for the second year students. So we talk about polynomial fits or some simple function fits like sine, cos, those kind of exponential function fits. So how does one systematically select? Suppose you have a data and then you are actually developing what I would call as a heuristic model or a black box model. This model is not really coming fully from physics. So this model, you have multiple candidate models. You might say, I want to fit a line or a parabola or a cubic equation. How do I choose between parabola and a cubic equation? Why cubic? Why not quadratic? Okay, so how does one systematically answer these questions? Okay, so that is what we want to see. And then when you get data measurements from the field, there is always errors in the data. So how do you deal with errors in data? What are the implications on the estimated model parameters? So what is the approach that is going to be adopted? Okay, so I just will take a few minutes on this. Well, what I want to do in each step, before I actually teach a concept, I want to create a need for that concept. Okay, I want the students to appreciate that, well, unless I want to create a roadblock saying that, oh, there is a roadblock. Now you need to think how to cross this roadblock. So unless we create a roadblock and then let them experience that roadblock, it is not possible that they appreciate why you need to cross the roadblock. Okay, if we just present that, take data, step 1 do this, step 2 do this, step 3 do this, then it's a procedure which is to be remembered and not the why I'm doing this doesn't get internalized. Okay. So this is an attempt to. So what are the activities and assessment? So I'm going to talk about think, pair, share. I think yesterday you had some taste of think, pair, share. Dr. Mrunal introduced to you think, pair, share. So I don't know whether we'll be able to do think, pair, share as part of this lecture. I will just hint that this topic can be discussed in the class as a think, pair, share. Okay, so because if we start doing think, pair, share here for this 1.5 hours is not sufficient. So this is, let's see if we can do something. So the first learning objective is to create a need for developing a empirical model in science and engineering. Okay, so I need to first emphasize that there is a need to do this. Okay, so I want to discuss a practical situation where a raw data cannot be used for design. Okay, raw data cannot be used for design. Now, I'll give you one or two examples, and then I have listed here more examples. But I have created scenarios. Okay, I have created scenarios which actually will emphasize that there is, you are stuck. Okay. Now my first scenario is, and then second thing that I'm going to use here is data visualization. Okay, that you actually encourage students to visualize patterns, visualize data, and then decide upon the model building. Okay, so my first example is the first hypothetical scenario that I have created. So I'm creating a story. Okay, this not that I have taken it from any book or anything. So you can create such stories. We can be creative. So this first story is, I have some circuit to be designed. Okay, and all of us know that the resistance of a, say, copper wire is a function of temperature. Okay, I want to place this circuit. I am designing some circuit, putting it in some device. That device is going to be placed some maybe in Rajasthan, maybe in Himalaya. Okay, the temperatures are quite different. Somewhere it could be 40, somewhere it could be minus 10, minus 15, minus 20. Okay, will circuit perform in the same way? Okay, in Rajasthan and in Himalaya, will it be the same thing? Okay, so this is the question. Okay, so what then do you do? You suppose you show this data. What I did was I created this data from, I know what is the temperature dependence. I could find out from the net what is resistance versus temperature dependence. I added random errors in the data and created data sets. Okay, so creating data sets for teaching is not that difficult. So now the question is that if I have this data, okay, there are trouble here. For example, I take this 60 degrees. Okay, one data point is here and one data point is here. Which one do I take and why? Yeah, so it is, and then I have something at 60 and then at 50, but suppose I want something at 47.5. What do I do? How do I interpolate and get a data in between? Okay, so I need to create such situation. Where students can appreciate that, well, something more than just having this data is needed. I can't just have this data. It is not useful. Okay, so I need to have some kind of dependence on a cause and effect. So this is my effect variable. This is a cause variable. How are they related? What, we need to discover that. Okay. Second example is another story saying that, a car company asked a team of engineers to design a new car. Okay. So they wanted to introduce a mid-size car. Okay. And these engineers collected data of different cars available in the market. Okay. So there is a crucial design parameter in the car, which is, I am not an automobile engineer. Okay. Creating such stories doesn't require any I am not a mechanical engineer. Okay. So creating such stories doesn't require any big background. Okay. So now the point is that this team of engineers was asked to design a car for engine displacement of 200. Okay. No data is available. Okay. And you can't say that, well, I'll do experiments. You have to design a car of 200, do experiments. It's not an affair where you can afford to do experiments. Okay, this is something available from literature, published literature. They have collected it, and now you want to say something about mileage when the displacement is 200. You want to sell this idea to your management that it will be good to have a car of displacement 200 because it will give me certain mileage. Now what mileage? Will it be 20? Will it be 23? Will it be 25? Okay, so it's you need to guess this. And then best way to do it is that take data available for other cars and then try to look at the pattern, and then using this pattern can you try to guess, give a educated guess. Okay, now there is a need for doing some modeling that relates this cause and this effect. There are umpteen such data sets available in the net. You can create by a little bit of thinking and writing some simple programs. You could ask your students to do an experiment on virtual labs, collect data. Okay, they could just log into a virtual lab, collect data, and or you have the device here. Yeah, can you show me? Nowadays there are simple devices available where recently we got this one simple device. Yeah. So one faculty from you can just keep this here. US has designed some simple experiment. There are two heaters here, okay, and there are two temperature sensors. You can actually connect this device, this simple system, to the computer. You can change the heating, and you get temperature measurement. Yeah, this thing costs $25. Okay, you can program it using C++, Python, all kinds of MATLAB, Scilab, all the codes are available. Doing an experiment using this takes about 10 minutes. Yeah, 10 minutes? 5 minutes? Yeah. So such devices, well, there is one virtual lab available in IIT Bombay. Professor Kandan Modgalya has created it. I don't know whether he'll get chance to talk about it. But there are some devices like this, some simple heating system with temperature measurement. Those are kept in lab here. You can book a slot on that system. There are 30 such devices kept on a stack. These are those ones he has devised are little bigger ones. You can actually book a slot, do an experiment, get data. Takes half an hour to get that data. Okay, so there are many things available on the net. There are many things available where you could actually create data sets for students, so they get a feel that they are doing something. Okay, they are doing some experiment to get data, real data. Okay. So I can create such situations. So there are some things I have listed here. This is global temperature rise scaled value versus year. Okay. Now the next question that I need to ask is that, okay, this is my data. Okay. What model should I fit? Can you help me? Why? Quadratic, what he's saying is dangerous, because if it is quadratic, then it is not a good news. I hope he is not true. Okay. If it is linear, yeah, but why linear? What is linear? What is linear? Constant rate of change. Slope is linear. Okay. But then quadratic model is also linear in parameter model. It's not a non-linear. It's non-linear in time square, time cube, but it's linear in parameter model. What is linear is also, okay, we'll come to that. Okay, so this is my data, and then now I could create a discussion in the class by asking what model I should fit. Okay, why did you think of line? Why didn't you think of sine and cos? Why didn't you think of exponential? There are no other functions that you have studied. Why line? But I could do, I could do Fourier series. I can do linear combination of. How do you now? Okay, good. All these are valid solutions. Okay. Now the question is, can I mathematically support this? How do I arrive at this decision that it is actually linear and not quadratic? Okay. By regression, I'll show you some fits, and then you'll be hard pressed to tell me which is the correct regression. Okay. So we'll come to that. Yeah.
Lower values of lower values of 1 and higher value of y, so that's why
So somebody might say quadratic, somebody might say it is constant over here, and then it started around 1940. ज़्यादा cars आने लगे तो ऐसे जाने लगा. Huh? So that could be a more industrialization, and so you could have two lines. Yeah, you could have two lines. Okay. We do not know whether this part was periodic here and then something else happened here. We don't know. So there are patterns. So now if we create a discussion like this, looking at the raw data, okay, here good thing is that none of you agree, which is good. Yeah, because then there is a scope for doing something more. Because then I can ask this group to develop a quadratic model, this group to develop two lines, and then we'll compare, fight lagate hai. Yeah, so that we can do which is good model, and then you have to have a basis for judging which is a good model and why it is good model. Okay, so I have created some other data sets, some reaction yield versus pressure temperature, and so now the thing that we need to do here at this stage is data collection, where there are multiple data sets available on the internet. Ask students to get those data sets, or you can buy such simple devices for your college. This is some 3,000 rupees, or you can use slots on virtual lab. You can ask students to do virtual lab experiments. Most important thing at this stage, before they proceed to do regression, is visualization. We should ask them to visualize data through MATLAB, Excel. Yeah, I think Excel. I don't know whether Excel can visualize data on mobile phone also now. Probably it can. It does? Oh, great. So I have not tried that. So you can ask students to do it in the class. That you put it on the Moodle, say that download the data set, okay, plot it in the Moodle and show me. Okay, so it is that simple. Okay, and then you could plan a TPS activity, think, pair, share activity. TPS, I have used this everywhere. I have used this short form. Think, pair, share activity, which is centered around patterns observed in the data. So what pattern do you observe? Okay. So we could create a discussion. Can you capture this pattern using some function? Okay, and so on. So does the relationship exist between yield and reaction yield and pressure and temperature? How do you capture it? And what if you want to do something in between for which data is not available? We have to emphasize here that doing experiments is very expensive. So extrapolating, interpolating using a curve fit is very cheap. Okay, okay. So next learning objective is selecting equation form. So I don't want to force on them what are the equation forms. Like you had different opinions. Okay, they are likely to have different opinions about what is the suitable form, and we could encourage them to. It's a good idea to say that okay, you develop this, you develop this, you develop this, instead of saying that this is linear. Okay, you find out whether it is linear or not linear. Okay, so we could have a programming activity. Now here, when I'm saying programming activity, it could be either two levels. Nowadays, data fitting can be done using Excel without requiring to know many things. Okay, so you could just do it in class using Excel app, yeah, and given some data. Or you could have programs like my colleague Professor Gururajan is going to explain today. So you could have computer-based activity where they actually do this. So now what we need to do is to ask them to, look at different patterns. Ask them to look at different patterns, plot those different patterns, and then try to say that, well, this fits or this fits or this, what do you think fits? Okay, so we can ask them to recollect all the mathematical functions, error function, and there are so many functions we study. Look at the patterns. If you ask students to draw, see, one thing that we find here, even for our MTech or PhD Viva entrance exam, is that many times if we just ask students to draw on the board, okay, draw y is equal to e to the power minus x. Okay. Many people struggle. They don't know what it looks like. Okay. So where do you start? What is the first point? So many times you have to keep prodding. Okay, what will you do if it is x is equal to 0? Okay. So they will start from some arbitrary value. Then you have to say, okay, x is equal to 0 means e to the power minus x is 1. So where you should plot. So you have to do this. So it is good that if they visualize patterns and then they do matching. So we could initialize some discussion in the class on, what pattern do you think you could. Then what we need to tell them, now is the point where they cannot guess. Now we need to take things ahead and then say that, look, expressions relating the dependence, exact dependence is not known. Okay, I don't know how global temperature rise and time is related, or I don't know how, even right now when I'm developing a model for resistance versus temperature, I'm not using physics. I'm just trying to catch a pattern. Okay, so what is the basis? Why some other equation can be used? That's where we need to connect with the maths. What is the foundation of doing all this? Is that, look, there is this famous theorem called Viesturs Theorem, which says that any continuous function can be approximated with an arbitrary degree of accuracy using a polynomial function. Any function can be approximated, any continuous function can be approximated. This is something that he proved way back, probably in 1850s or 1860s, about 175 years back. And this has far-reaching implications in so many fields. Okay, in numerical analysis, in science and engineering. So invoking this theorem, okay, I can actually, it gives me a foundation, it gives me a basis for saying that, well, I can choose a polynomial approximation. Okay, so which polynomial approximation? That is not what Viesturs told you. He just told you that, you can approximate any function using Viesturs theorem. So this is the input that we need to give them. But which polynomial approximation? Okay, so should it be linear or quadratic or cubic? What does it depend upon? So this needs to be explored. Okay, so there are many such examples that are there. You may have temperature dependence of specific heat of gas at a constant pressure. That is a function of temperature. Which one is the correct model? Depends upon the range in which you are fitting the model. Okay, in some range this model might be correct, in some range this model might be correct, or more appropriate. I won't say correct, more appropriate. Okay, better representative of the data set, and so on. So there are many such situations in chemistry, in thermodynamics, in this is physics, electrical engineering. Okay, so there are many such situations, and then what we could do if you are teaching this course in third year or second year, end of the fourth semester, we could ask them to go and hunt for, there could be an activity saying that just go and hunt for such correlations that you have encountered in other courses in your department course. Okay, just go and find what are the correlations. Where did you hit upon these correlations? So that itself will tell them that this idea of polynomial fitting or correlation fitting is used in many engineering applications, in science applications. So this could be a activity that is. So still we haven't talked about regression. We haven't talked about fitting. Okay, I'm just talking about So now at the end of all this, I'm going to say that, look, what we are looking at is an abstract form where y is some effect, okay, and there are some causes, x1, x2, pressure, temperature, whatever, there are some causes, and this is a mathematical model that relates effect with the cause. Yeah, so that is where it's a bad idea to begin with this. It's a good idea to arrive at this through multiple examples and say that, this is what I want to do. Okay, now that, I have come to a point where we have decided to fit some polynomial. Okay, and we have data. Okay, now how do I go about? So now I need to introduce least squares. Yeah. So what is least squares method? Minimizing the error, square of the error. Minimizing the least square. No. Minimum is the least square. Minimizing the sum of the square of errors between what? What we expect. Actual or measured minus desired. Measured minus average. Okay. But desired, if you know, then you don't know what is desired. I'm looking for one more word. Most probable probably comes close, yeah. Predicted minus, model predicted minus, not actual. We don't know what is actual. See, if I get a measurement of temperature in this room, okay, if I put a sensor, if I get a measurement 22.7 degrees at this location, can you say that true temperature at this location is 22.7? Measured temperature is 22.7. Yeah? It is, you can say it is close to 22.7. You cannot say the true temperature is 22.7. Okay, so there is some problem. Okay, so now, so I want to solve the parameter estimation problem and then use this to pose new problems. Okay, I want to pose this to solve the parameter estimation problem and then use that to create new difficulties so that, there is motivation to go further. Okay, so we have to, in between, do activities to create new difficulties. Okay. I want to convert this into a matrix equation, okay, so that I relate to, see now I'm trying to relate to something that they have already learned. They do a course in matrix algebra, okay, so I want to relate all this to matrix computations, okay, so that they realize that all the course on linear algebra and matrix computation was very much relevant. It's not, okay, and then I also want to introduce this concept of non-uniqueness of the solutions. Okay, of what you get from doing this exercise. Okay, let's go back to hydrocarbon example. Okay, and then I start. I want to fit this quadratic equation. Deliberately, I am choosing a quadratic equation, not linear equation. I'm choosing if I want to choose a linear fit, I just have to delete one term. It is not that difficult. Okay, so this is data is available from I have taken it from some book, and now I have some 8 data points. I have 8 data points. Yeah, and I want to fit a polynomial that is boiling point as a function of carbon number. Carbon number changes from 1 to 8. Boiling point changes like this. I want to actually develop a model that is quadratic model. Okay, now. Can you solve this equation? Why can't we solve these equations? How many equations are there? How many unknowns are there? Not 4. How many unknowns are there? 3? There are 11 unknowns. Why there are 11 unknowns? See, there are errors. This is an approximate model. This is not a perfect model. This is not coming from chemistry or physics. This is a heuristic model. Okay, A is not known, B is not known, C is not known. Okay, what about V1? They are not known. Okay, so how many equations? 8 equations, but 11 unknowns. Okay, so we could actually discuss, can this be solved? It can be solved. Why? Why can't, she's saying it can't be solved. How many of you believe that it can't be solved? All of you believe, then you have to tell me how it can be solved. Yeah, it can be solved. Yeah, I believe it can be solved. My hand is up. Your hand is up, right? You said yes. You said no. Can't be solved. I see. Anybody who thinks this can be solved? It can be solved. How many solutions are there? Yeah. Why? Some parameters can be arbitrarily chosen. Yeah. Suppose you make an assumption for arbitrary reason that this is 0.01, 0.02, 0.03. Three errors are, I arbitrarily choose. Don't ask me why. Okay. I have three more equations now. V1 equal to 0.01, V2 equal to 0.02. Yeah. V3 equal to minus 0.02. Three equations. So, 8 plus 3, that makes it 11. 11 equations, 11 unknowns. So it can be solved. But the problem is there are infinite solutions. So how do we choose? How do we go ahead? Now there is a problem. Okay. If I collect more data points, will that solve the problem? Okay. Let me take another data set. This is, yield is extent of a reaction. You take some chemical A going to B, and how much of it is converted into the product. What is the percentage converted to the product. So there is some chemical company is interested, and they have done experiments at different temperatures and different pressures. This data set is for 45 different combinations. Okay. Now I write, I want to fit this model. I want to fit this linear model, not quadratic. I'm just fitting a linear model. Okay. A plus BT plus CT. E is the error. Okay. E is the error. And I should have written V there. So now again the same problem. I have 45 equations. Unknowns are 3. Okay. So 48. So whatever I do, I take more data points, I still have the same problem. Yeah. The number of equations is always going to be less than the number of unknowns. So I need to do something now. Okay. Can it be solved? Yes. It can be solved. If you fix 3 parameters out of those 45 arbitrarily, okay, it can be solved. You will get some solution. Whether that's a good solution, bad solution is a different story. But it can be solved. Okay, number of equations become equal to number of unknowns. It can be solved. Okay, so we need to discuss this aspect of solvability, because this probably is discussed in the maths course in a very abstract way. When can you solve a set of equations and so on? Whereas here it actually is a real problem. I have linear equations. Are these linear equations, by the way? Are these linear in unknown? What is linear? Huh? Homogeneity and additive. So are these linear equations as far as the unknowns are concerned? What are unknowns here? Is n unknown? So n square is known, n is known. Okay. So in terms of unknowns, A, B, C, and V1 to Vn, these are linear algebraic equations. These are not nonlinear equations. Okay. So okay. So one could do a TPS activity. I'm cutting it short on how many possible solutions exist. Then what I need to do is, I need to do a little bit of a generalization, because I'm not going to solve a specific problem in one domain. So I have this reaction rate model, I have this yield versus reaction model, and then I have this model with resistance and temperature model. I'm going to map it to a generic model. I'm going to define, there is some cause x. This cause gives rise to these functions f1x, f2x, f3x, and then I write this generic model, y is equal to theta1 f1x plus theta2 f2x. Yeah, and here I have a cause variables, pressure and temperature. Okay, and then I have functions, f1x is 1, f2x is t, f3x is p, and then this model can be written in this generic form. Okay, both the models, one is linear model, other is quadratic model, all of them collapse to one generic form. y equal to theta 1 z1 plus theta 2 z2. It's a linear model. z1, z2, z3 are known. Yeah, I don't know theta 1, theta 2, theta 3 and v. Yeah, so everything, all these models collapse into. So then this is not something we can ask them to guess. This probably we have to do in the class and say that, well, it's now sufficient to work with this. It's sufficient to work with this. So I'm going from particular to generalization rather than generalization to particular examples, which many times never get taught. Okay, so now my problem is, if I have data of y1 to yn for different values of causes, z1 is a cause, z2 is a cause, z3 is a cause. Okay, I have different values of z1, z2, z3. How do I estimate theta 1, theta 2, theta 3? So now what I'm going to do is, so this is a generic problem. This is a generic problem. I'm just taking 3-parameter problem. Okay, I have, now we need to, before we proceed further, we need to do a activity in the class talking about what are the possible sources of error. What are the possible sources of error? Why is this V term here? Measurement error? Yeah, measurement error is a good thing, yes. Then? Instrument error is measurement error. Yeah, we can, yeah, that's a correct answer. Measurement error. Then? Human error. Okay. But human error is measurement error. No, so reading error, measurement error. Then, what are the possible sources of error? Huh? No, there is. Huh? Modeling? Error in the model, yeah. This is what I was looking for. Approximation error. Am I saying it correctly? Yeah. So, there is an error because you are approximating something. Okay. So, you are approximating some behavior using a polynomial. So, there is an error coming from approximation. Even if there was no error in the measurement, would there be an error still there? Because of approximation. Because we are fitting a curve. Okay. So, this is not an exact relationship between n and boiling point. Okay. So, we need to do an activity here to discuss about what could be sources of error. Okay. If there is an error, okay, now then there is a problem. Okay. If there is an error in measurement of yield, okay, why there is no error in the measurement of temperature and pressure? There could be error in the measurement of temperature and pressure. Yeah? If there is error in the temperature pressure, there is error in Z1, Z2, Z3. Yeah? Okay. Then we have to say, well, what you say is true. Because some smart student will always say that, well, if you say that there is an error in Y, which is this, what about error in P? P could be wrong. Yeah? T could be wrong. Then well, we have to say that, look, that problem is more difficult to solve. I'm going to solve a simple problem which says that all the errors are blamed to one term called V1. I'm not going to look at error in measurement of pressure. I'm going to assume that pressure is perfectly known, temperature is perfectly known. Okay, there is only error in the measurement of Y or approximation error. Everything is coming in V. Okay. So once we do this, once we explain that we are making some simplification, okay, the next thing is, say that now, well, I would want the errors to be as small as possible. Okay, I would want the errors to be as small as possible, but there are multiple errors. So what I'm going to do is minimize sum of the square of errors. Yeah, I'm going to minimize sum of the square of errors. Now, minimizing sum of the square of errors, will it give me 3 more equations? What I need is 3 more equations. What I need is 3 more equations. Yeah, 3 parameters are unknown. So in the case of pressure, temperature, yield, there were 48 parameters, 45 equations. I need 3 equations. In the first case, I needed 3 equations, 11 parameters and 8 equations. So, well, what you have here is you get those 3 equations because at the maxima or the minima, the derivative has to be equal to 0. Let's assume that the students are mature enough to know that derivative should be equal to 0. It is now taught in 12th standard, at least for single variable functions. So now this 3 more equations and 45 other equations, 48 plus, 48 unknowns, 48 equations, we are done. Okay, we can solve this problem. Okay, so now there is a unique solution. Okay, now to solve this, I'm going to introduce matrices because that makes computations very, very easy. Okay, so this set of equations I'm going to convert and write like this. Okay, I'm going to write this as a matrix equation. You can do these manipulations very easy in Excel if you teach them to do look at everything as a matrix equation. So this same equations can be written as one matrix equation, y is equal to a theta plus v. Yeah, and the problem of finding out minimizing some of the square of errors is just minimizing v transpose v. Okay, I'm not going to teach you least squares, so you could do all this least square parameter estimation. The solution comes out to be a transpose a inverse into a transpose y. That's the solution, where y is this vector, a is this matrix. Yeah, and then you can write this solution. This is for any problem. You can this, and then you can teach this algebra of how to differentiate a matrix, a scalar function with respect to a vector and all that. If you teach that, that is, I'm not going to teach that. Now, what is the computing activity? Now that we have taught them this, we need to create a computing activity. The computing activity is that they have collected data sets, done visualization. Okay, ask them now to fit that, find the parameter estimates. Okay, and we can give tasks to different, we could divide it into groups. We can say that group A, data set so and so, global warming, do linear model fit. Group B, do quadratic. Group C, do cubic. Okay, and then we'll plot all of them together and see which one is giving better data. Okay, so you can estimate model parameters using MATLAB or Scilab. Encourage them to write their own programs. Other possibility is that, okay, if you want to do it quickly in the class, ask them to use Excel. Excel will give you fits and give you different curves, and you can show it very quickly in the class, whichever way you prefer, depending upon the time that you have available for you for doing the activity. But this is a computing activity that can be on the same data sets which they have collected and visualized. Okay, so that is very well. It's good to give problems here from different domains. Okay, so that they know that this can be applied to variety of problems. They get a new data set tomorrow, they'll be able to apply this. Okay, now I need to do an assessment here. Now this is a good time to do quiz. Okay, and because now you have covered some formulae by which you can do calculations, hand calculations. Okay, so you could actually now do a quiz. Okay, so before that we have to do a written tutorial. So what we do typically here is that we'll give them a tutorial problem sheet, and then we have a class in which we just go around with TAs, or sometimes there is no TA. I just go around discussing with the student groups what are their difficulties in solving the specific problems. So I just say that, okay, in this tutorial, problem number 7, 9, 14 are difficult. Let's solve them collectively. Okay, somebody has solved it, you help your friend. Okay, so that's how, and that creates lots of discussion. Okay, and that helps them to understand. And then, of course, you could then devise a quiz, written quiz based on the tutorial. So this is a good point to do a tutorial and quiz. Well, now we have asked students to do this. So you ask them to fit data, and then see that, well, linear doesn't seem to be a good idea. This seems to be going up. Yeah. So linear, I don't know. So you can have people fitting different models, and then ask them to compare what they think is the correct way of representing. Okay, but then visualization does help. This was the data set for yield versus pressure and temperature, and the identified model looks like a plane. Okay, you can, if you extrapolate or interpolate using the identified model, this is the linear model that you identify between pressure, temperature, and the yield, and then it's a plane. And this geometrical visualization is very, very important. Yesterday, Professor Verma said there are 3 pillars of teaching mathematics for engineers: geometry, algebra, and computations. This is a course where everything comes together, geometry, algebra, computations, visualization. Okay, now, next activity, now I want them to appreciate that the job is not done. Okay, so what if you actually have devices of, suppose I have a physics experiment in which I can maintain the resistance of a copper at different temperatures, and I can estimate the resistance using multimeter. Okay, you give this to the student groups. Each group every week performs an experiment. Okay, or we can actually create those data sets in the computer and then give it to the students, and then ask them to in the class we give them different data sets for temperature versus, and then each one got a different result. This is what you see when you do experiments in the labs. Everyone gets a different fit. Now the question is, which model is correct model? Which is the correct model? Which one should I pick? Let's say you plotted this. Which model is correct model? Both are line fits. Now you said that I should fit a line here. Okay, we fitted a line. Which line is correct line? Which one should I use? My predictions are going to change drastically if I choose one over the other. We have to compute the least squares errors. Okay?
So the sum of squares of the errors, whichever is the least, we can use it.
Okay, so that's a possible solution. Okay, I will now give an experiment in which this part will get defeated. Okay, these students did experiments at every 5 degrees. I'll ask one group to do experiments at every 2 degrees. There are 50 experimental data sets. Okay, some of the squares will be more because there are 50 errors now. Here there are 20 errors. Okay, now what? So sum of the square of errors is not something related to sum of the square of errors we need to do, but sum of the square of errors alone is dependent on upon the number of data points you choose. No, so I need to tell them that look, the parameters are dependent. You could do this numerical experiments. You give different data sets to the class, and one gets 100 data points, other gets 50, other gets 25. Estimate model parameters. Because somebody has 25, the model is bad, but sum of the square of errors is small because there are 25 data points. And there are 100 data points, there are more number of errors. Okay, so now I need to find out a quantity which is average sum of the square of errors. We have to drive them towards variance, concept of variance. Okay, and this could be done by doing, you change the A matrix, you change the points at which you do experiments, you change the errors in measurements, the estimates will change and each one will get. Now, one thing that they need to say is that all of them are correct. Okay, can I give a band in which you expect the values to lie? Can I come up with a band in which? So now there is a need to go beyond just least squares. Okay, because you have a problem. The second problem, so we could do a TPS activity here, is that, what is the true value? What is the true value? Which is the true set of parameters? Okay, so everyone is getting a different answer. Okay, so now we need to go beyond just fitting a line. Okay, so there's a need to look at something more. Okay, so there is some uncertainty in the data, okay, which is causing this. Can you quantify this uncertainty? So now I need to go beyond algebra optimization and look for something different that is not been taught till now. Okay, second question is, yeah, which model is the correct model? Is it actually going like a line, or is it going like a curve? Yeah, quadratic. But I should suppose I fit a cubic. Okay, will cubic be better than quadratic? No. It turns out that I'm going to show that cubic is not better than quadratic, and I'm going to mathematically show that. How do you mathematically show this? How do you mathematically argue that this model is not good and this model is good? Okay, so what I want to do is, yeah, here, which, by the way, which one do you think is the correct model? Quadratic? अरे नहीं यार, 50 साल में पूरा खत्म हो जाएगा. Let's hope that it is not quadratic. Okay, so now the question is, can I argue? Now we have to pose this question. Okay, we can initiate discussion in the class. Say, look, this seems to be close to 0. Is 10 to the power minus 5 close to 0? How do we say something is close to 0? How do we systematically say that something is close to 0? So, well, this is 10 to the power minus 5 because this is t square. That's why it is minus 5. Okay, so can I say that because this is small, I can neglect this term? What is small? How do you systematically say something is small? So unless this difficulty is faced, you cannot go further and then create a need for statistics. Okay, so that is where I need to do something about. So we need to create a need for statistical approach so that they can they see that there is a point in doing this. So how do I screen between multiple candidate models? How do I use identified models for a prediction? Now, if your estimate themselves are uncertain, the predictions are going to be uncertain. Resistance predicted is going to be uncertain. Okay, car mileage predicted is going to be uncertain. Okay, so how do you quantify the uncertainty? This is where statistics is going to help us. That's what we need to. So this need has to be arrived through, doing some programming experiments, comparing results of different people, and then making them realize that now there's a need to go further. Okay, we can't stop here. Okay, now the next learning objective is create motivation for using statistical tools. Okay, so can we develop a model for the error? Till now we were only developing model for resistance versus temperature. Can we develop a model for the error? Okay, so this is the next thing that I want to introduce. This is the next learning objective. Okay, and then I want to derive expressions for parameter covariance. Now the maths becomes more and more involved, and the maths part I'm going to skip and then concentrate more on the active learning part. As I said, you can always go to my notes. And then, so now we need to make an assumption about the error. Now the question comes whether is this true, and so on. Students will have always these doubts. Okay, but then we have to tell them that when we do modeling, okay, we make modeling assumptions. Okay, there is nothing like truth. Okay, so for example, if I start modeling this room, okay, I have to start making assumptions. One simplifying assumption I could make is that the temperature in this room is uniform. There's only one temperature. Okay, this is a simple modeling assumption that there is one single temperature inside the room. Whether it is true or not true this might be a useful assumption to solve some simple problem like what should be load of AC that I should choose for this room. So for solving that, this might be enough. Okay, but if this was a semiconductor facility, okay, and then it is important that zone should be cooler and this zone should be hotter and whatever, okay, then I better not say that this is one uniform temperature. Okay, I better model, this, I make an assumption that this zone temperature is different, this zone temperature is different, this zone temperature is different. I do a different model. Okay, so we can develop levels of models. We make simplifying assumptions because they help us in solving certain problems. So this is a simplifying assumption that error is zero mean and variance sigma square. Okay, so I'm making this simplifying assumption so that I can solve the problem. Then I'm going to make one more assumption that all the errors that I encounter in the data when I do multiple experiments, all of them are identically distributed. All of them are coming from the same distribution. Okay, so it is for the one error in the first experiment has mean 0 and standard deviation sigma square. Even the second one has the same thing and the third one has the same thing. So this is a simplifying assumption. Is this true or false has no meaning. This is an assumption that helps in modeling. Okay. And then we make another assumption that Z1, Z2, Z3 are perfectly known. Now the problem is finding out theta 1, theta 2, theta 3. We are going to recast the problem in the language of probability statistics. Okay, so now I'm going to write this as a equation. This y is a random vector, is a vector of random variables. This theta are some true parameters. A is a matrix which we already introduced to them, and v is a random vector. Okay, if each person does different set of experiments, actual values that you will get for this are different. Actual values that you will get for this are different. As a consequence, the estimate will be different for every person. Okay, so this is a random, because this is a random vector, this becomes a random vector. Because there are errors, random errors in the measurement, the results obtained are also have random character. Okay, so now then I just go on showing properties of this. What is the what is the, how do I find, if I know variance, see suppose I know variance of V, the next question is, can I quantify variance of theta, estimated theta? Okay, so this algebra let us skip, you can look into my notes for the algebra, that's not so important. What is important here is that you show that, you show that the covariance of theta, the possible errors in theta can be found by this expression. So we do algebra in between and derive this. So this is a in-class derivation and lecture, and this the students cannot guess this. Okay, so this has to be taught. Okay, so actually, just to connect with yesterday's lecture, Professor Jugal Verma talked about Gauss and fitting, data fitting. I'm just doing a extended thing of the same thing. Okay, so he gave one example of the first time it was done for not a planet. What was that? Comet, for a comet. A comet for one particular comet, Sirius or something. Yeah. So so how do you find out the parameters of the model? So you find out using this. So that is then what is the uncertainty associated with the parameters, so that you can quantify explicitly. Now next question comes, okay, this is uncertainty associated with the parameters. What is the distribution? What is the distribution? How do you talk about distribution of this? Okay, so then instead of telling them that use this distribution, use uniform distribution, use this distribution, we need to make them realize that how we select that form for the distribution. So what I'm going to do is an activity. Okay, so activity that I'm going to do is to ask them to plot histogram of errors. So there are two different models. One is quadratic model, other is linear model. Okay, on the same data set. Okay, you ask them to find out the error between measured and model predicted. Not true. We don't know what is true here. Okay, the model prediction minus the measurement. Okay, you find that and then do a histogram. Okay, this is real data. Global temperature rise, real data. I have not done any fudging. I have just taken the data fitted. So what do you see here? What pattern that you see here? Can you guess what should be the distribution that I should use? Normal distribution. Yeah, I should use normal distribution. So if I look at this pattern, in fact, when you do least squares, what happens in least squares is that it favors smaller errors and it penalizes large errors. Least square penalizes errors symmetrically, positive, negative error square, it doesn't bother. Okay, so you normally, if you actually do least square fitting for most of the data sets, you will get patterns like this. Histogram will look. Okay, if they look at this histogram, okay, then it is easier to convince them that let us choose normal distribution. Okay, let us assume that this thing has a normal distribution, and then you could do a. So we could do this activity in the class where different now we have groups. They have different data sets. They have fitted different models. Each one of them you can ask that draw histogram of the errors. Okay, and my expectation is that all of them will look like bell shape. Okay, the data set is larger, then they're more and more closer to the bell shape, and then we connect that this has a normal or Gaussian distribution. Okay, instead of telling them the solution in the beginning, if they have this activity of looking at the histograms, creating a histogram in Excel is, I think, 2-minute job, right? Have you done it anytime? You just say this column minus this column and hist or something, and then it gives you histogram. Okay, so it's so easy to create histograms. Okay, so then you connect to the maths and say that central limit theorem tells you that when the errors are coming from multiple sources, Gaussian distribution is the best choice, and so on. Okay, but now they have seen it, in different examples, different engineering examples, this thing happening, so they can connect it much better to the Gaussian distribution. So why Gaussian distribution is no longer a problem? Well, then what you do is, of course, how do you use this Gaussian distribution? If I have this Gaussian distribution, I'm not, if you are more details of this derivation, you can look into my detailed notes which I have uploaded. But then once you have this Gaussian distribution, you can actually show that each parameter has, error in each parameter has a Gaussian distribution, and then using that, using that we can actually find out. So this I'm skipping. I'm not interested in the derivation part. But then what I show is that the parameter estimate, okay, is a Gaussian distribution that algebra you can work out, and say that it is some true parameter into this variance. So this is what you actually derive expression for density function of the parameter. Okay, and then then the next question is that, okay, I found a density function for the parameter. How do I use this to do something in my in the models that I have developed? Okay, so I'm going to do hypothesis testing. Now here at this stage, my courses were towards the end where I have already taught them hypothesis testing. So I'm going to do an application of hypothesis testing. So what is the hypothesis? Okay, first is that I want to give bounds in the range in which the truth can lie. Okay, and this I can find using this Gaussian density function. Okay, again, I'm just skipping this technical part, which is T distribution and Gaussian distribution, so that you can look into. But what is important is that now I can go back and say that the parameters of this model can lie in this range with 95% probability. The theta 2 will lie in this range for the quadratic model. Okay, 95% probability that it will lie in this range. So you can come up with those bounds. Okay, what is the possible for the resistance temperature experiment? Okay, you can ask each group to come up with the bounds, okay, in which the parameters can lie based on the data set they got. Okay, so the estimated parameter was this, but each group will now say that, well, I got this estimated parameter, but it could lie between this upper bound and this lower bound. This is my estimated value, but somebody else's answer could be anywhere between this and this. Okay, so each one can give a bound on where they think the solution can lie. Okay, so they come to know that, look, I got a line, but this line is uncertain, and I can quantify that uncertainty. Okay, so this is again connecting with what group activity we have created. Okay, so well, I did test whether the quadratic model. Now, how do I say whether quadratic model, this term is close to 0 or not? is 10 to the power minus 5 0 or not equal to 0? Okay, so I'm going to test a hypothesis. I'm going to do a hypothesis testing that, my null hypothesis is that ith parameter is 0. My alternate hypothesis is that it is not equal to 0. Okay, and then there is a systematic procedure which you can derive because you know the density function now for the parameter estimate. Okay, and then you can test this hypothesis. Okay, so this is if you apply it to the global warming example. Okay, I'm going to test this hypothesis. The quadratic term is not equal to 0 against quadratic term is equal to 0. Okay, because what is 10 to the power minus 5? Is it equal to 0 or it is not equal to 0? Okay, so now if I do this systematic procedure, mathematical procedure, okay, then I can come with the conclusion that there is a strong evidence, unfortunately, there is a strong evidence that the quadratic term contributes and global warming might be exponentially rising. Okay, so there is, those who are gunning for the quadratic term, okay, are probably true. Okay, so here I could do a summative assessment. I can give so now I have taught all the concepts that I want to teach. Okay, see, because when I'm doing this hypothesis testing, okay, actually I have taught them model selection. Whether I should go for linear model or quadratic model. Quadratic model seems to fit better, but I had doubt whether this term is 0 or non-zero, this coefficient is 0 or non-zero. Okay, now systematically I am able to say that, well, this term doesn't seem to be equal to 0. It makes sense. Okay, so I have taught all the concepts that I have wanted to introduce, and now I could do a final assessment. One possibility is to give a group project. Okay, and then ask them to do everything from first to last. Okay, that is a possibility. The other possibility is to give a programming quiz. This is what I do. I give them a programming quiz. The word quiz here is little not quite correct, because I tell them that I'm going to ask you to do this, 5 things. Prepare and come. Okay, so they know what the question is, except, one fellow might get temperature data, other fellow might get, some global warming data, third fellow might get some other data. The data sets, what is Y and what is X will vary, but that doesn't change basic ideas, right? So that is, so this could be, so aim of this examination now is to cover all the concepts together. And in this data, analysis course, we give this exam as a programming quiz, not as a handwritten quiz, because data sets are long and you can't sit and do hand calculations beyond a point. So you have done one quiz, which is hand calculations, okay, and then you do the second quiz, which is programming quiz. So, in which everything is covered. So this is just a I'm just revisiting this quiz. So in this quiz, I do ask them to do fitting 2 kinds of models, this model, this model, this model. Then I ask them to compare different models, give confidence intervals on the parameters, then test the hypothesis for the quadratic model, whether this is equal to 0 or not equal to 0. So it turns out that quadratic model, the theta 2 or theta 3 is not equal to 0. So null hypothesis is rejected. But when I develop a cubic model, okay, it turns out that the fourth term is not contributing. Now this is very nice thing to show here, because I want to say that 0.5 is 0. Yeah, I want to prove using statistics that 0.5 is not contributing, 0.5 is 0. So my null hypothesis is that theta 4 is 0. I'm getting some value which is, arbitrary value because of data. And it turns out, if you do the analysis, that, we reject the null hypothesis. So this term is not contributing. Okay, so 0.5 is actually 0. Okay, means it is close to 0. It's some random value which is coming. So you can actually show here that 10 to the power minus 5 is not 0, but 0.5 is like 0. Okay, so then you just tell at the end of the lecture that, well, what we have done in this set of 2-week lectures, this takes about eight lectures, 2 weeks of teaching, is, that this model development from data is happening for last 300 years. Many people have been doing this. So what we have done right now is just touch tip of the iceberg. Okay, but then hope this quick, movie that we had in last 8 lectures, it gave you a good idea of, how modeling is done, and it will help you in your professional life. So in summary, well, what is important is to give a guided exploration. Okay, to do a guided exploration. So this is teaching regression in an exploratory mode. At every point, we give them data sets, we ask them to explore, okay, and then we pose a difficulty. Then once we pose the difficulty, we create an in-class discussion. Then we give some solutions, partial solutions. Then we create a new difficulty. Okay, after that new difficulty, you solve it, then you create a third difficulty. So you go on creating new hurdles, and then you go on solving them. Okay, and this makes the learning experience better, because every time they are doing something, they are experiencing the difficulty. Okay, and these days making that happen through computer simulations, virtual labs, to all kinds of data sets available on the net, it's not that difficult. So it's a guided exploration. Okay, it helps me to talk about the physics part of it. It helps me to talk about 3 mathematical concepts, or 3 areas in which they have done courses. One is, concept of optimization and linear algebra. Okay, I didn't talk about one more aspect, geometry. Okay, and what we are planning to do is to share a book with you. नहीं आ रहा क्या वो? ऐसे. Yeah, we at least have plans to share this Gilbert Strang's book with you, because we think that it's one of the ideal book written which covers different aspects of maths teaching, algebra, geometry, applications, and computations. There's some uncertainty in getting the book before you leave. Okay, so and probability statistics. So through activities and hands-on activities, and I'm able to actually teach concepts from linear algebra, from probability statistics, from optimization, and bring them together with applications. And this will help them to understand those concepts, those abstract things which they studied. Actually, there is a lot of if you go through Strang's book, he talks about least squares and projections, and he relates them to ideas which are taught in the 8th standard textbook, and then builds on that to talk about geometric ideas associated with this, and gives a very nice geometric insight. So there are many things that, many facets of this you could bring, but what you bring through these hands-on exercises is far more valuable than just going linearly and then doing it deductively and doing the applications at the end, or giving all the problems which are in X, Y, Z, where they can't relate it to anything. Yeah. So intermittent activities which create hurdles, and those hurdles are solved by new theory. That is the arrangement of lectures. And then, as we said, I talked about assessment of 2 types, both formative and summative. Summative assessments are 2. One is a handwritten quiz in between, and at the end there is a programming quiz. Where summative assessment is one which you use for grading. And formative assessment, I have written all TPS activities that you can conduct throughout the course. That is one formative assessment. And the second formative assessment or semi-formative assessment is tutorials. So you have to have tutorial sessions, computing tutorials or programming tutorials. So at least two sessions of programming tutorials are needed. 2 or 3 sessions are needed to do this. And some of the things now you can do on a mobile phone. Yeah. the things that you can do on a mobile phone. So those could be in-class activities. You don't have to discourage students from bringing their mobile phones. So I encourage them to bring their into the class. I ask them to say that, okay, now you open my model notes. Okay, so like that, so they're using it for, or you ask them to go and search for this thing on the net, on this resource. So they are engaged in actually using it for your class. So that is better than saying that. So this is a book which is a very good book, and these two are very nice references on teaching. So if you go to Moodle, I have been doing a monologue, so I would be happy to answer any questions. So what I have uploaded, of course you can see on Moodle, I have uploaded tutorial sheets, both programming tutorial sheets, then computing tutorial sheets. Then I have uploaded my, what I would call as dense notes, which are just talk about the entire mathematical development, if you are interested in that. And I have uploaded these notes where I have put up a story of how to put it in an active learning mode. Okay, so that, yeah. So questions till we go for. Correct. Yeah. So there are some assessment indices. For example, there is a criteria called archaic information criteria, or there is something called Bayesian information criteria. Okay, where you can actually do a balance between overfitting and number of model parameters. What happens is if you go on increasing the number of model parameters, yeah, then you seemingly get less and less sum of the square of errors. Okay, but then that creates funny patterns, yeah, and then you can actually make the students fit those models and then show them that you start getting funny patterns due to overfitting. And then you relate it to this archaic information criteria, which is a numerical criteria to screen the models. Okay, so we can look at the visual patterns that you get if you start overfitting and the archaic information criteria, and then say that now use this to decide upon your, yeah? Yeah, yeah. Curve fitting, yes. Yes. Well, since both of them are using, see, if the data is same, and if the equations are same, you should get the same solutions. Yeah, but you can ask them to compare, because maybe Excel is using different method to estimate the model parameters, and then if there is an option of using some different, instead of least squares, if they say that least absolute value, sum of absolute value, instead of square they say least sum of absolute value. Okay, or you can develop that model which gives you least maximum error, and so on. There are different ways of formulating the problem. Okay, so if that is there, one can compare. Yeah, that's a good idea. Yeah. Any other question? Yeah. So if there are no questions, let's go for a cup of tea. We can discuss it there if you don't want to discuss it.